Today, under the course CEC 412, Alternative Transportation System, we will look at airport pavement design. The first thing we'll look at is Federal Aviation Administration design procedure for flexible airport pavement. Flexible pavement design is based upon the CBR method, that is the California Bearing Ratio method, an essential empirical method. The design assumes that 95% of the gross aircraft weight is carried on the main landing gear assembly and 5% on the nose gear assembly. We've already highlighted on this before. So the gross weight of the aircraft, 95% goes to the main gear assembly, while 5% goes to the nose gear. Next, we look at the steps of FAA design procedure. The first thing is to obtain forecast of the annual departures by aircraft type. The second one is to determine for each type the required pavement thickness using the appropriate design curve with the forecast number of annual departures for the aircraft. The third step is to select the aircraft requiring the greatest pavement thickness as the design aircraft. And then the fourth one is to convert the annual departures of all aircrafts to the equivalent annual departures of the design aircraft by applying the following formula. The formula we have here, which is equation 1, log REG is equal to log R subscript I multiplied by F subscript I multiplied by bracket open W subscript I over capital W, then close bracket raised to power 0.5. So here, REG is equal to equivalent annual departures by the design aircraft, while R subscript I is the annual departures of aircraft type I, which means this very one, the first one, is for the design aircraft, which is the aircraft requiring the greatest pavement thickness. Then I can be any other aircraft apart from the design aircraft. So if we have 5 aircraft, including the design aircraft, it means REG is for the design aircraft, while our subscript I is for the remaining 4 to convert them using the previous step where we said convert the annual departures of all aircrafts to the equivalent annual departures of the design aircraft by the formula which we have here. So F subscript I is conversion factor. It will be given. Then W subscript I is the weight load of aircraft type I, which is any of the other aircraft apart from the design aircraft. And capital W or W is equal to wheel load of design aircraft. So next we look at pavement thickness requirements. Here we have figure 1 to 3. It said are the FAA design charts for different aircraft types. The charts have incorporated the effect of load repetition, landing gear assembly configuration, and the wandering, which is lateral distribution effect of aircraft, with subgrade, gross weight, and total equivalent annual departures of design aircraft as input. The total pavement thickness requirement can be read from the appropriate chart. Each design chart also indicates the required thickness of bituminous or asphalt surface course. So let's look at the graph we're talking about. This is one of it. This very one is for, we said here in figure 1, is critical area flexible pavement thickness for a single wheel gear. So this method is a CBR method. Having the CBR method in mind, the CBR value in mind, this is the CBR value. You can see 3, 4, 5 up to 50. So if the CBR is 5, And also having in mind the gross weight of the aircraft, these lines that we have here are lines showing the graph of the gross weight of the aircraft. And the other ones we have, this very one going this way, this very one is for the annual departures. And you can see for the annual departures, we have 25,000, 15,000, 6,000, 3,000, and 1,200. For the gross weight of the aircraft in pounds, here we have 75,000, we have 60,000, we have 45,000, we have 30,000. Also note here, it is said that 1 inches is equal to 2.64 cm and 1 pound is equal to 0.45 kg. So with this, you can be able to convert from inches to centimeter, and then from pounds to kilogram. Also note from this graph, it said the curve is based on 20-year pavement life. And for thickness of bituminous surfaces, we have 4 inches critical area and 3 inches, use 3 inches non-critical area. So once you have your CBR of your pavement, be it the subgrade, the subbase, the base course, what the next thing you need to have is the gross weight of your aircraft and then the annual departure. So with it, if the CBR is 5 and the gross weight is 60,000, as you can see here, this red line here is showing that the CBR is 5 and the gross weight of the aircraft is 60,000. And the annual departures, if you look at where this red line is pointing, is for the third line, we have 6,000, as you can see here. So we move it down and then trace what is the thickness of the pavement. You can see in between 20 to 30, this should be within 26 or 25, 26. So this is what we're having here. This is just as an example, but this note that the chart is not the same for all aircraft type. For all aircraft types, we have the ones for the single wheel gear. We also have you can see the next one here we have here is it says critical area flexible pavement thickness for dual wheel gear. So you can see this very one is still the same pattern. You have your CBR, you must have the gross weight of the aircraft in consideration. Then you also need to have the annual departure so that you can be able to read the pavement thickness. The graph is almost similar, but not exact. The pattern of reading the graph is the same, but the values or what you read out from the graphs are not the same. So use the appropriate graph for the aircraft type under consideration. So you see the next one, the third figure we have here says critical area flexible pavement thickness for dual tandem gear. So you can see that we have for single wheel gear, we have for dual wheel gear, and we have for dual tandem gear. So next, we look at, it says the minimum base cost thickness is obtained from figure 3.4. That's the next figure we want to look at. The FAA requires stabilized base and sub-base courses to be used to accommodate jet aircraft weighing 45,000 kg or more. These stabilized courses may be substituted for granular courses using equivalency factor in table 1. So you can see the minimum base course thickness requirement that is needed for our pavement thickness. We have, you can see total pavement thickness here, and this graph, these graphs that we have here, you can see for subgrade CBR of 4, 5, 6, 7, 8, and up to 20. So this is pavement thickness, then this is the CBR value. that we have here. So here we have the thickness is in this very one is in inches, and the one at the vertical line is the equivalent, which is the one for in centimeter. So it is the minimum base course thickness requirement. You can see the equivalency conversion factor for the factor for conversion, just as we said earlier, that stabilized base course may be substituted for granular courses using the equivalency factor in table 1. So we're looking at the table, while that of the 3.4 or figure 4 is the minimum base course thickness. So we get the minimum base course thickness here from this graph. Then from this very one, we get the equivalency factor for stabilized base course and also for stabilized sub-base course. So this is where we get the values from. So here we said this is the FAA recommended equivalency factor for stabilized base and sub-base. The FAA suggests that the full design thickness T be used at critical areas where departing traffic will be using the pavement of 0.9 T used at critical areas receiving arriving traffic such as high speed turnout, and 0.7 T will be used where traffic is unlikely. These reduction in thickness are applied to base and sub-base courses. For pavements receiving high traffic volume and exceeding 25,000 departures per annum, the FAA required that the bituminous surfacing be increased by 3 centimeter and the total pavement thickness be increased as follows: 104, 108, 110, and 111% of the design thickness based on 25,000 annual departures. For annual departures of 50,000, 100,000, 100,000, and 25 and 200,000 respectively. So we need to consider that the pavement thickness is not the same. So critical areas will have thickness will be increased based on what have been already said here. So the areas that are not critical will lower the thickness to make the construction economical. So the next thing we look at here is we look at an example of how to perform this calculation. We have aircraft types. You can see here B727 100, 727 200, 707 320B, DC930, and B74700. So these are different aircraft type. Then we have these are their landing gear type: dual. You can see dual tandem, and you can see the rest dual and also double dual tandem. So we are considering about 5 different aircrafts. Their average annual departures are given here. You can see their annual departures. We have 4,500. We have 9,900, 3,200, 5,500, and 1,200. So maximum takeoff weight. Maximum takeoff weight in kips, which is pounds per square inch. So you can see here we have 160 for the first aircraft, 190.5 second aircraft, then 327, 108, 700 for the third, fourth, and fifth aircraft, respectively. So these are our question or our the input data that we have, and we're expected to design a suitable pavement, flexible pavement using FAA method for these aircrafts given here. So the next thing you can see, we have other things that factors we need to consider. It said determine for each aircraft type the required pavement thickness. So we've already been given that we should assume that the subgrade CBR is 10%, the base course CBR is 80%, and the sub-base CBR is 30%. So Using the table that was given to us initially, which is this table, we now extend the table, have another column, because you can see initially we are given aircraft type, landing gear type, we are given annual departures, we already have this, and also the maximum takeoff weight. You can see it here. This is what we have here. You can see they've already been given to us. So we are going to add, we have one, two, three, four columns. So we have to add the fifth column. And this fifth column is the total pavement thickness in inch. Where do we get this value from? We use the graphs that were provided initially to read out the total pavement thickness for each of the aircraft, considering the aircraft type, as we said earlier. So you can see from this graph, for the single wheel gear, we consider is CBR, it is given CBR, we consider the thickness using the CBR and the annual departure. So you can see for the first one we have here, this one is aircraft of dual type, and this dual type, the annual departure is 4,500. Maximum takeoff weight is 160 pounds. So 160,000 pounds. So so here we have the fifth column, which we are adding. We are trying to read the total pavement thickness in centimeter, inches or centimeter. You can see the values are in inches, while the one in bracket are in centimeter. So we get this from this graph that we considered earlier, these graphs. So we read it from there for each aircraft. And we can see for the first aircraft is considering the annual departure, considering the aircraft weight, you can see the annual departure, 4,500, 160,000 for the aircraft weight, but in pounds, but in keeps it is 160. Then the landing gear type is dual. So let's look at the graph and see how we can possibly get the value. So this one is for single whale. Let's look at for the one of the dual type so that we see if we can be able to pick it up from there. Having this first aircraft is having an annual departure of 4,500 and 160,000 keeps. So, and it's a dual type. So for the second one, we have annual departure of 9,900, and we have the takeoff weight of 190,500. This very one we have here, or 190.5 in keeps, 190,500 in pounds per square inch. So we'll go back to the graph. That this one is for double tandem. We're looking for dual wheel. So we go to where we have 9,900 CBR value of 10, where we have 9,900 annual departure, and then we have 190,000. It's between 200 and 150, very close to 200. So we read from here down here, and then to where we have annual departure of 9,900, which is between 15,000 and 600 and 6,000. So it should be somewhere here. So we read down on this graph. If we read down from here, you see, because this is 10 CBR, we move down to 190, which is close to 200,000. Then move horizontally and trace where you have 9,900, which is in between the third line and the fourth one, because the fourth one is 15,000, the third one is 6,000. Then you move down here, it should be around 28 point something. So if we go back to our table, see that what we have there is we have 28.5. You can see it here. So this is for the second aircraft. Then the third aircraft is that of dual tandem type. We note the annual departure, which is 3,200, and the maximum takeoff weight of 327,000. Let's move and see if it is correct on the table and see what we have. This one is, they said it's 26. We'll go back again and verify. So we have 3,200, 327. So we'll go back to the graph, 3,200, and then 327. So we'll go back and then read down here. We have 327. It shouldn't be slightly below 400,000. It should be slightly above 300,000. So here, read it down here and then move down to second from here. Move down to second to the third one. So you will see that if you're able to place your ruler, because you read down here and then move it down to this point, you will see that you can now read the value from here down, which will give us around 26 point something. So let's go back to the table and see what we have. You can see here we have 26. The third aircraft is 26, which is 66 in centimeter, 26 inches, and the equivalent is 66 in centimeter. So we check for the last one, which is also of dual tandem type. So it has annual departure of 1,200, and the takeoff weight is 700,000. So we'll go back to our graph. 700,000 dual T. So this is a dual T graph, as you can see, dual T. Here 1,200 annual departure, and then it has the one of 700. You can see the maximum that we have here is 400. So we can use 400 for any weight that is above that. So here we move down from 10 to where we have the graph of 400, where we have 400, this is 400. Then we try to point to where we have 1,200, which is the second one we have on the line here. So we move down here, touch 400, and then move up to where we have this second line. Then we move it down because this is 10 to 400. Then we try and touch this and then move down. We should have a value that is less than 30 something. So here we have on the table, you can see we have 27.27, which is 69. So we've been able to get the total pavement thickness. When comparing this total pavement thickness, we'll see that the first aircraft is 19, second one is 28.5, third one is 26, fourth one is 19, fifth one is 27. So the one having the greatest thickness is that of 28.5. So this one will control the design. So this will be the design aircraft, irrespective of the fact that the weight is not the greatest. Takeoff weight is not the great, but the annual departures, you can see here, it has the greatest annual departure. So it is able to produce or requiring the greatest pavement thickness. So we'll go to the next, what we have to look at here, the next table. Here we already have these things, these values are given to us. We have the aircraft type from our data given initially, then their type. This is the aircraft type, this is their conversion factor for each type. Then this is the annual departure, which is given to us here. And then the maximum takeoff weight was given also initially, but we also need to compute this additional table, the single wheel load. How do we get it? Because we have the main gear assemblage and the nose gear. So the main landing gear, using the initially we are introduced to different aircraft type of, like this one we have single wheel gear. This very one has two main gears and one nose gear. double dual tandem has two main, two two tires or two wheels for the nose gear, and then other landing you can see for the main landing it has 4 plus 4, which is 8, 8 plus 8, which is 16, total of 16 wheels. So this other one, dual tandem, has two. You can see it has two no wheels on the nose gear and 8 on the landing gear. This other one, which is dual wheel landing gear, example is this C6. So it has 2 for the nose and then 4 for the main gear or landing gear. So with this in mind, we can be able to get these values on the table here. For the first aircraft, it is just of dual type, and since it's of dual type, the maximum takeoff weight is 160. So 160, we go back to the this figure we have here for dual wheel. We can see dual wheel has 2 for nose and 4 for the main landing gear. So we have 4. So we are going to, what we will do now is to obtain this value 38, we will look at the gross weight, which is 160,000, and multiply it by 95%, because FAA specifies that 95% of the weight will go to the main gears, while 5% is to the nose gears. So 0.95, which is 95%, multiplied by 160 divided by 4. So once we're able to do that, we'll get 38. So if you still want to do for the second or the design aircraft, what we need to do is to multiply 190.5 by 0.95, which is 95%, and divide it by, this one is still dual, which is 4. It will still be 4 since it's dual, the dual type, aircraft type. So we still need to divide it by 4. We multiply 0.95 by, which is 95%, by 190.5 and divide by 4. Then for this double dual, so we'll go back to the table or the figure we have here so that we'll be sure of, for the dual tandem. The dual tandem, we have double dual, we have dual tandem. Dual tandem has 8 gears. So what we need to do is to go back for this very one, which is the dual tandem type. We are going to multiply 327 by 0.95, which is 95%, and divide it by 8, which will give us this value. This very one is for dual type. We multiply 108 by 0.95, 95%, divide by 4. Since it's dual, it's 4 waves. Then the dual T, can say dual DT, double tandem. This very one is still, we multiply it by 700 by, multiply 700 by 0.95 and divide by the appropriate waves that we have here. You can see for the double dual tandem, we have 4, which is 8, another 4, which is 16. And then, so it means we are going to multiply 700 by 0.95 and divide by 16 for us to obtain 41.25. So we can also verify that. We try and search through our calculator so that we'll be sure of what we have. So let's open our calculator app. Let's be sure it is correct. So for the first one, you can see that we said 160 multiplied by 0.95. We have 152 divided by 4. What do we have? 38. You see, this very one is correct. So the second one, what we do is to multiply 190 by 0.5 by 0.95, which is 95%. What do we have? We divide it by 4. we have 45.24. You can see it is correct. Then we also go back, and for this very one, which is dual T, we said it is 8. We said 327 multiplied by 0.95, and then we divide it by 8. What do we have? 38.83. You can see it. Then for the other one, it's still the same with this very one, which is dual. We do it by 4. Then the last one, let's verify the last one. The last one is 700 multiplied by 0.95. What do we have? Divided by, set 16. What do we have? 41.25. Okay, we have 41.56, which is still close. That is how we're able to get our single well load. So let's minimize our calculator app. Then we'll continue. On the next, you can see the conversion factors for dual tandem 1.7, double dual tandem is 1.7. That's why on this table we have 1.7, as you can see, double dual tandem. Then for the dual tandem type. So we continue. You can see on the table now, we have our aircraft type. We have conversion factor for different these. We already have this. We have this very one, annual departure. Now, remember from this formula, you can see from this formula, we need to get the annual departure by the conversion factor. So that's what we have done here. Multiply this annual departure by conversion factor. You can see 4,500 by 1. We have this. 9,900 by 1. We have this. We have 3,200 by 1.7. You can see what we have here. Then we have 5,500 by 1. This is what we have. Then this one, 1,200 by 7. You can see what we have here. So this is the total of what we have, which is 27,380. So for the single wheel gear, we already got in it. We got it in the previous table. So we already have this. Now we need to get this value, which is here, which is the gross weight of the aircraft under consideration divided by the gross weight of the design aircraft. So you can see our design aircraft here is the one that control the design, the second one. So what we are going to be doing is, for this very one, you can see for the single, since we have gotten the single whale here, we have 38. We divide 38 by 45.24 and then get we'll get the square root of it, or raised to power 0.5. So let's try that with our calculator app. We'll go back to our calculator app and verify what is here on this table. So here we have, you can see we have 38. So we say 38 divide by the design aircraft, which is 45.24. What do we have? 0.899. So this is what we have. We need to get raised to power 0.5 and know what the value will be. So we need to get 0 raised to power. Okay. So here we get the square root of the answer. So we said 38 divided by 45.24. 45.24. What do we have? 0.88. So what is the square root of the answer? You can see what we have here, 0.917. So this is what we have. So the square root of it is this. The same thing as 0. Raised to power 0.5 is still the same thing as the square root. So you can see what we have here is similar to this. So the next column, which is the equivalent annual departure by design aircraft, arrow subscript EG. Here we can obtain this using this formula. which is in step 3 here. It says log average equal to log I subscript I multiply by F subscript I. Close the bracket, multiply by W subscript I over W. Close the bracket, raised to power 0.5. So this, as we've already explained this before, so we now need to substitute. We now, for the first aircraft, which is B727-100, we have the wheel load. We've already obtained this, so we just fix this value here, 0.9. We bring out our calculator. We have a calculator using before, so we use this calculator. Now we want to get what we need to do is that we already have this value here, which is rho subscript I multiplied by F subscript I. We have it here, 4005. We multiply it by this 0.917, which is this, raised to power 0.5. So we multiply this by this. But first of all, we have to find a logarithm of this value. So we find a logarithm, back to our calculator. We say 4,500. 4,500, the logarithm of it. This is what we have. We multiply it by 0.9, 0.917. This is what we have. So I have this value. We have to convert it. We have to find the antilog of this. So we have, for us to obtain the antilog, press this value. So we have 2238. You can see what we have here. This is supposed to be 2238. It's close to this. We have 2220. So this is the antilog of this value 1. So we go back to the next column. We have 3,200. That is 5,440. 5,440 was the log. Then we multiply it by 0.752. Multiply by 0.752. What do we have? This is what we have. So we find the antilog. The antilog is 644. Here we have 655. They are close. So once you've been able to fill up this table and get this total, you pick up this value you have here and then go to the graph, because we have a CBR. We are given initial CBR value from our question. You can see subgrade CBR is, for the subgrade, is 10%. So with the value we've gotten on the table, this value we have here, the total equivalent annual departure by design aircraft, we sum all of them together, we have this. So what we now need to do is to go to the table and then we have critical flexible pavement thickness for dual wheel. So the aircraft is of dual wheel type, as you can see when we investigate that aircraft, we see that it is of dual wheel type, so the design aircraft. So go to the graph with the 16,536 that we've gotten. We go to the table under CBR value of this. So we check the gross weight of the aircraft. The gross weight of the aircraft, which we had today, as 190,500. So since it is 190,500, what we need to do is to go to the graph under 10 CBR for the subgrade, which is 10. We move down and touch 190,500 is close to 200,000. We move down to where we have an annual departure. We are talking about an annual departure of 16 535, which is what we have here. So we now move down from here, bit slightly below 200,000, which is 190,500. Move down. We touch this because you can see from the graph, the last one here is 25. The second to the last is 15,000. So between 25,000 and 16,000 and 15,000, we have 16,500, and which is what we have it add here, and 36. We have this value here. So we move down and check what we have. We'll have a total subgrade value of roughly 30 inches, because what we have here is 30. So this 30 inches is equivalent to 76 centimeter. So we've gotten for the subgrade. The next thing we need to do is we now get from back to our question here, or the data that was given to us. We can remember that our base called CBR is 80 and the sub base is 30%. We already used these to obtain our pavement thickness. So we go further to get the thickness for other layers. So here we have the asphalt and base thickness. How do we find that? We were given our CBR here for our sub base as 30. So we go back, go to the graph where we have for that same graph type, critical area flexible pavement thickness for dual wheel. Under 30, we move down since our sub base is 30. So we move down, and as we're moving down, we have to touch our annual departure for our aircraft. Remember that it is 190, which is close to 190, 500, which is close to 200,000. So we move down and touch where we have the graph of 25 and 15,000, which is close to that of the 16,000, the 15,000, 16,536 that we have here. So once we're able to touch it, we move down and read the value we have, which is 13. What we have here is 13.5 inches. So which is equivalent of 34 centimeter. So this is what we have. So since we have this value, we go again and to the next graph where we have our, because we have our, from here you can see we said asphalt plus base is thickness is 13.5, which is what we got here. Now what is that of the asphalt from this 13.5? We were given the base called CBR from our data here as 80. We'll go to the next graph, 80%. So we'll go to the next graph, which is this. Here we cannot read 80 because the maximum here is 50. So we'll take that of 50, move it down to where we have 190.5, then touch where we have, that is for the gross weight, and then touch where we have 16,300 and 535, which is what we had on the table. So we read it here. It will, we will now be able to read down to get 8 inches, which is 20 centimeter. So if we minus that 8 inches from the 13 we got earlier here, so what we'll have is 5.5 inches, because here we said that asphalt plus base thickness. So when we remove the asphalt, the remaining base thickness will be 5.5 inches, which is 14 centimeter. So with this, we now check, since we have gotten our base, but we need to know the minimum base, because since what we have here is 5, we have a chart also for to obtain the minimum base thickness. It was given to us earlier. I think we viewed it before. This is what we have, this chart here, which is figure 4. So we'll go back to this graph and we try to get the minimum. So we try to get the minimum. So we try to get the minimum. Here we have our total pavement thickness, and here we have our CBR value, minimum base thickness, and here we have, okay, this is our subgrade CBR. So remember our subgrade CBR today, we got it, it is 10 from the data given to us. You can see it here. It was given to us as 10 subgrade CBR. And the total pavement thickness, we got it today as, let's see what we had. That total pavement thickness as 30 inches or 76 centimeter. So we go back to what we have, and CBR with CBR of 10, total thickness is 30. You can see from here 35, we have 25, we have 20. So 30 falls in here. We try and touch our, you can see this line, these are different subgrade CBR. So our own is 10. So as we move it straight, we touch where we have that of 10, and then we move down. We have minimum base course thickness should be 15, but we had 5.5, so we'll adopt 15. So this will give us a design summary of, you can see asphalt layers 8 inches, which is what we got from here. You can see 8 inches from here. Then we also have base course is, the thickness is, for the base course is 15 inches. We had 5.5, but the minimum should be 15 from what is recommended by FAA, and is equivalent of 38 centimeter. Then we have sub base, which we had today. The sub base CBR, we had to minus it from 13.5, which is 16.5, because we had sub base CBR today. You can see we had, for the base, we had 13.5. So we minus it from what we have from the total, which is 30, which is 16.5. And then the total thickness will now be equal to 8 inches plus 15 inches plus 13.5, which is 39.5. In centimeter, it is 20 plus 38 plus 42, which is equivalent of 100 centimeter. So this is how to design flexible pavement using the Federal Aviation Administration design procedure.